At the center of modern baseload power generation sits a machine designed to convert immense mechanical rotation directly into continuous electrical energy. This is the TVV1000 2T3 three-phase synchronous turbo generator. Looking at this digital dashboard, the raw output metrics define the scale of the operation. Driven by a steam turbine at a constant 3,000 revolutions per minute, it yields 1,111 megavolt amperes to produce a full 1,000 megawatts of active power at 24 kilovolts. And it achieves all of this at 98.9% efficiency. As the display updates to show the resulting current, we hit the machine's primary constraint. Producing a gigawatt of power simultaneously forces 26,729 amps of electrical current through the stator. That high efficiency rating of 98.9% sounds nearly perfect, but at the gigawatt scale, the remaining 1.1% translates to massive thermal waste. Without continuous, aggressive heat extraction, the internal components would reach their melting points in minutes. The sheer acoustic energy generated by this process is also extreme. To manage the physical vibration and sound, an anti-noise hood encloses the unit, dampening the acoustic byproduct to below 90 decibels. Operating at this threshold means the TVV1000 2T3 operates as a tightly integrated thermodynamic, mechanical, and protection system forced into a precarious, continuous equilibrium. Passing through the gas-tight steel casing reveals the two primary structural bodies, the central immovable stator core and the high-speed rotating shaft. This cross-sectional diagram details the stator winding architecture. It utilizes a three-phase setup with two parallel circuits. The double-layered conductors use a double star connection. Zooming in to a single slot reveals both solid copper conductors and hollow copper tubes to facilitate direct internal fluid cooling. The rotor shaft itself faces severe mechanical constraints. To survive the immense centrifugal stress of spinning at 3,000 RPM, the entire body is machined from a single solid steel forging. The rotor's excitation winding is seated within the slots of this steel body. Standard copper would warp under these combined forces. Instead, the winding is manufactured using copper doped with silver, which maintains strict mechanical stability at the rotor's maximum working temperature of 115 degrees Celsius. To prevent the silver-doped coils from tearing outward under centrifugal load, they are secured in the body slots by duralumin wedges, locked down by heavily reinforced retaining rings at the end portions. Every material, from the silver-doped copper to the duralumin wedges and hollow stator bars, is selected specifically to allow the core to survive its own violent electromagnetic and rotational forces. Heat removal requires a trimodal cooling architecture. This schematic traces three independent fluid loops. The blue path tracks demineralized water flowing directly through the hollow copper stator conductors, circulating at 200 cubic meters per hour to strip heat from the slot internals. Because this water touches the live conductors, its purity is critical. The demineralized water must maintain a specific electrical resistance of at least 200 kiloohms per centimeter. If the resistance drops, the 24 kilovolt output would short-circuit straight through the cooling loop. The green path tracks the core cooling loop. Centrifugal fans mounted directly on the spinning rotor pull pure hydrogen gas, pressurized to 5 kilograms per square centimeter, forcing it through diagonal vent ducts. To reject this heat, the hot hydrogen cycles through 4 internal gas coolers, positioned at the end parts of the stator casing. These use bimetal tubes, smooth German silver on the interior for water flow, and ribbed duralumin on the exterior to maximize gas contact area. Using pressurized hydrogen presents a critical sealing paradox. The gas fills the stator casing, but the rotating shaft must physically pass through the external shields, creating a massive potential leak path for explosive gas. The yellow path shows the mechanical solution. The generator uses hydrodynamic pedestal bearings paired with forced pressure ring-type oil seals. Oil is pumped into a pressure chamber at the external shield, forming a physical liquid barrier continuously blocking the hydrogen from escaping. Pushing a gigawatt of power relies completely on this simultaneous orchestration, isolating high-voltage copper with ultra-pure water, aggressively circulating pressurized gas, and sealing boundaries with forced oil. To induce the magnetic field, the main rotor requires a massive continuous injection of 7,600 amps of direct current at 400 volts. Transferring 7,600 amps from a stationary source into a steel mass spinning at 3,000 RPM using physical carbon brushes and slip rings would cause catastrophic friction and electrical arcing. This split-screen diagram maps the brushless excitation scheme using an inverted alternating current synchronous generator coupled to the main shaft. First, DC power feeds into the exciter's stationary field winding, inducing an alternating current across the gap into the rotating armature. By putting the armature on the spinning shaft, the three-phase AC power is generated natively within the rotating reference frame. There is no need to bridge the gap with physical contacts. The alternating current must be converted back to DC before it reaches the main rotor. Two sets of rotary rectifiers, arranged in a three-phase bridge circuit with 30 diodes each, handle the conversion while spinning at full speed. Each rotating diode is protected by a series fuse to isolate short circuits. Additionally, RC filter units, acting as snubbers using resistors and capacitors, absorb commutation over voltages. The resulting 7,600 amp DC current is then routed straight down an axial bore through the center of the main shaft, flowing along the flat copper bars directly into the generator rotor. Brushless excitation solves the mechanical friction problem entirely by generating and rectifying the necessary control power on the rotating mass itself. The induced 24 kilovolt output exits the stator via 3 heavy-duty line terminals located at the bottom of the exciter side. Transporting this load requires isolated phase bus ducts built from thick aluminum. They are rated to carry 31,500 amps continuously and engineered to physically survive the violent electromagnetic forces of a 560 kiloamp peak short circuit. This schematic details the critical node between the generator and the 400 kilovolt grid, the GE FKGA8 generator circuit breaker. Using pressurized sulfur hexafluoride gas at 0.95 megapascals and a forced air cooling system, this breaker is capable of physically severing a massive 105 kiloamp fault current in exactly 75 milliseconds. Its operation is governed by an extensive relay protection matrix. This includes systems like the ANSI 87G longitudinal differential protection, monitoring internal stator faults, and the ANSI 40 relay, which watches for any loss of excitation that could throw the machine out of step. During a localized generator fault, the breaker trips to isolate the machine. However, it strategically leaves the unit auxiliary transformers connected to the 400 kilovolt grid, allowing the plant's essential cooling and oil pumps to pull backward power and coast down safely. Generating the power requires immense rotational force, but preventing an internal fault from cascading into total plant failure relies strictly on the precise mathematical timing of the bus ducts and SF6 switchgear. When the unit is synchronized to the grid, none of these systems function in isolation. Every loop, seal, and relay operate simultaneously, in real time. The inverted exciter magnetizes the rotor at 3,000 RPM, inducing a continuous 24 kilovolt surge. At the exact same moment, the highly purified demineralized water and pressurized hydrogen tear through the core to extract the aggressive thermal waste. Downstream, the sulfur hexafluoride breaker monitors the line, equipped to safely extinguish 105 kiloamps of fault current in fractions of a second to protect the larger electrical network. The TVVV1002T3 is an exercise in extreme equilibrium. It relies on the flawless orchestration of metallurgy, fluid dynamics, and high-speed power electronics to successfully sustain the gigawatt threshold.